material for our Math 1431 class, Calculus, for the spring 2020 semester here at U of H. And this video contains a discussion that's all about rules of integration. This is material from section 6.3 in our notes. And before getting on to any particular sorts of rules that we want to practice using, I actually want to start off these notes with a summary of the fundamental theorem of calculus. Sometimes I call it the fundamental theorems of calculus because there are two parts. So summary of the fundamental theorems of calculus. So maybe what we called Part 1 said the following: if you start with a function, usually denoted with lowercase letters, little f say, if this function you start with little f is continuous, then the area accumulation function, capital F of x, given by keeping track of little f's area, is an antiderivative for little f. That is to say, the derivative of capital F, I'll put it like this, the derivative of capital F at x is little f at x. And then a second theorem, fundamental theorem of calculus, says that if f is, again, continuous on, say, an interval from a to b, then you can use an antiderivative of little f to evaluate its definite integral. So, I'll even remind you of some notation I used last time. Sometimes you could use this notation. And I just have to tell you where capital G is an antiderivative, so where G prime equals little f of x. So these were our two theorems, and if you sort of think about it, what maybe just in shorter words what part 1 is saying is something like this, and I'll maybe write this in a different color. The derivative of an integral is the original function. You have to take a little bit of care when making this precise, right? Because in this phrasing, right, we're really talking about this integral stopping at a variable stopping point x. So once you set that up carefully, then indeed it is correct to say that the derivative of an integral is the original function, right? So we could even sort of say this part like this. If I took an x derivative of what I named capital F of x, so here I'm not even writing a capital F anywhere, I just get little f. For part 2, it roughly says that the integral of a function, little f, the integral is an antiderivative And it's really an antiderivative evaluated at 2 points. But you can imagine, maybe I'll write this in red, imagine that I ask you, hey, why don't you integrate up the values of some function, of not just some function, but maybe integrate up the values of somebody that is already a derivative. Well, part 2 says, if you want to evaluate this, you don't have to use rectangles. Just go and find a function whose derivative is the function I wrote there, g prime. So an obvious one would just be, we'll just use g. Its derivative is g prime, right? And so it's, in this sense, this version, what I've written here, is really saying the integral of a derivative is the original function. Right, so this is the sense, if I sort of think of what these two statements are saying in blue and in red here, one says the derivative of an integral is the function, the other says the integral of a derivative is a function. And so what we have here that gets sort of planted firmly in our brains is this idea that integrating and differentiating undo each other. They're sort of inverse processes. And I think I might post an additional video maybe in a few days that goes into why or how this works. So I think that's maybe coming a little bit in the future. But for right now, to finish up these notes, let me go ahead and put in a new page here. Okay. So what I kind of want to start with for today's notes is really a definition. And so this is what we might call the indefinite integral. And this definition really only makes sense, arguably, it makes best sense to introduce this after you've talked about the fundamental theorem of calculus. So after we have those two statements for the fundamental theorems of calculus part 1 and 2, then we can talk about the indefinite integral. And here's what it is. We write it, it's an integral sign, and then we write f of x dx, or whatever the variable is, tsu. But notice there are no limits of integration. So it's not saying take an integral from 1 to 3. It just says integral of f of x dx. This is called the indefinite integral of f of x. And what this is recording, this is all antiderivatives of f of x. Not just one of them, all of them. So let me show you an example to maybe contrast this. So let's say we had a definite integral from 0 to 1 of x dx. Right, so this is not an indefinite integral. This is a signed area. But we can try to compute this signed area using the fundamental theorem of calculus. So maybe I'll say in green, let's compute this using the fundamental theorem of calculus, specifically part 2. So we need an antiderivative for the integrand. That is, we need an antiderivative for little x. Which one do we need? As we sort of mentioned last time, there might be multiple antiderivatives, Well, keep in mind the fundamental theorem of calculus, part 2 says, well, you just need any of them. Pick one. And so here's a great moment to pause this video and see if you can find a function whose derivative is x, if you can find an antiderivative for little x. Alright, so here is my attempt at finding an antiderivative. You'll notice that x squared doesn't quite work. This is not an antiderivative for x. How do you know? Because when I take a derivative, I don't get x, I get 2x. So this is close to a right answer, but it's not quite what I want. Instead, I'm going to divide this by 2. And now when I take a derivative, I will get 2x over 2. The 2's cancel, and I'm just left with x. So this is a good antiderivative, and what I can say is that the definite integral from 0 to 1 of x dx, that's just my antiderivative, x squared over 2, evaluated at my endpoints of integration. So this will be 1 squared over 2 minus 0 squared over 2. That'll just be 1/2. So that's the definite integral of x, say from 0 to 1. But now let's consider the indefinite integral of x. This is not going to be a number. This is going to be a bunch of functions, right? If I scroll back up and tell you what I told you a moment ago, this notation for the indefinite integral refers to all possible antiderivatives of the function little f. So this refers to all possible antiderivatives of the function little x. Well, and we can say, well, I wrote 1 down because I found 1 for my work just a moment ago. It's x squared over 2. But there are a bunch of other antiderivatives, right? For example, you may have thought of x squared over 2, but it's possible you thought of x squared over 2 plus 7. Why is that an antiderivative? Because when I take a derivative, I'll still get x from differentiating the x squared over 2, but then the 7 differentiates to 0. So I'll still get x, right? This will still work out to x. Okay, so here's the trick, and some of you may have seen this or heard of this. We basically have all antiderivatives once we found 1. All other antiderivatives are the one function we wrote down plus any other constant, which we'll call c. So this is what becomes, in students' mind, the main difference between a definite integral and an indefinite integral. For indefinite integrals and definite integrals, you will use an antiderivative, either to plug in the endpoints or to write down one antiderivative. But if you're a definite integral, then you plug these numbers, these limits of integration, into your function and get a number. If you're an indefinite integral, you write down the one function you could think of, and then you say plus c. This plus c gets you all other possible antiderivatives. They all differ by a constant. And so what these notes are about, at least in part, is going through all the different rules we might have for computing or figuring out all these antiderivatives. So let me show you one important one, which may or may not be written down below, but you're certainly expected to know this. Let's write down, maybe in green, all possible antiderivatives of x to the n. So we did x to the 1 a moment ago. And you can think about, how would I think of an antiderivative of x squared, right? And to do this, right, we want to write down all antiderivatives. We want to undo the power rule. There's a power rule when we differentiate, right? The power rule when we differentiate says, bring the power down, then decrease by 1. That's the differentiating power rule. Well, to undo this, we're going to do it in backwards order and do the opposite, right? So rather than subtract 1 from the power first, rather than subtract 1 from the power last, we're going to add 1 to the power first. And rather than multiply by this power, we're going to divide by it. And because this is an indefinite integral, I need to always put a plus c to acknowledge I've undone. To acknowledge that I have all the antiderivatives. So here's the good news, though, about coming up with these rules. You can always check whether or not you're right. And so let me just try a check here in red. How do you check that you're right? We're saying that this thing over here on the right is an antiderivative for this guy, x to the n. Well, to check that, I just need to take a derivative. So I'm going to take a derivative of x to the n plus 1 over n plus 1. And how does my differentiating work? Well, the power comes down. I subtract 1 from the power. A constant stays out front, but it got canceled, and so I got x to the n. So this rule I wrote in green is a rule you should absolutely have in your back pocket. You're going to be expected to know how to do this in a short amount of time, just quickly. So we'll practice some examples in a minute, but I want to make one exception, or want to note one exception. In my formula above, I had to assume that this power was not the number -1. And I'll let you think about why that's true. You might want to look at this denominator to think about why I was assuming that. So we need a formula for, if we want all possible x to the n's, we need one different one when n is -1. And the formula might look a little bit different. Can we think of an antiderivative for 1 over x? That is, can we think of a function whose derivative gives us 1 over x? And we just talked about a function like that. That's the natural log function. Because this is indefinite, I get to put a plus c. Okay, so there are other rules like this, and we're going to practice them down below. But these that I've written in green so far, you definitely want to make sure you're comfortable with. All right, let's see what our typed notes have in store for us. Okay, so there are typed notes. You should read this. They're just reviewing the fundamental theorems of calculus. And here we go. Here, our notes talk about the constant rule for integrals. What's written down below is technically an indefinite integral, right? Because there's no limits of integration. And you can even see they have the plus c. Let me go ahead and, since I've written all over this, what they're saying is that the indefinite integral of a constant. Well, can you think of a function whose derivative is a constant? Sure. How about the constant times x? When I take a derivative of this, I'll just get k. Because this is an indefinite integral, I need to write down a plus c to say I've now got all my antiderivatives. Okay, so here's an example. Example 1, we can work these out. A says, okay, what is the indefinite integral? I'm just checking, it's indefinite, no limits, of 10. Well, that should be 10x, but if you don't want to lose a point, don't forget to put your plus c because, again, it's an indefinite integral. All right, here's another good one. What is the definite integral of the constant pi from the interval 1 to 4? And you can do this two ways. They're both pretty short. the way we're sort of having you practice do it right now is we want you to use this rule that an antiderivative for pi is pi times your variable. And I'm just going to show you the different ways you can notate that. And so you plug in the top limit, so you get 4 times pi. You plug in the bottom limit, you get 1 times pi. You subtract them, and you get 3 pi. Of course, you could also do this thinking visually about this, right? You can always, and probably should always, keep in mind that a definite integral is an area. Maybe signed area, but it's an area. So you're talking about an area from 1 to 4 underneath a flat line at height pi. Well, that area, that's just the height times the width, so that's just pi times 4 minus 1. So that'll also be 3 pi. For most of these questions, we won't be able to do it visually, right, because our graphs will be very curvy. But for this one, you could think visually. Okay, so here's our power rule that we just rehearsed above, right? It says the antiderivative for any x to the r is under the power rule, so it's x to the r plus 1 divided by r plus 1, all plus a constant. And then they say, oh, make sure your constant was negative 1, your power. So let's try example A here. What is the indefinite integral of x to the 4th with respect to x? Okay, well that's just x to the 4 plus 1 divided by 4 plus 1, and then plus my constant. So that just becomes x to the 5th over 5, all plus that constant. Okay, example B may look a little trickier, but I promise it's not. Right? We want to find what's the definite integral from 0 to 1 of 1 over square root x dx. And here's the thing, as we did when we were first differentiating these functions, it can be really helpful to write the square root as a power. That's x to the 1/2. And then we have x in the denominator, but that can be written as a negative power. So now we're ready to use our power rule, if you will, our inverse power rule, because we're anti-differentiating. So keep in mind that the antiderivative of x to a power dx, as long as that power isn't negative 1, is x to the n plus 1 divided by n plus 1. And that's an indefinite integral, so I put plus c. But I'm going to apply that here. From 0 to 1, x to the negative 1/2 dx. Here I'm using n is negative 1/2. And it's not negative 1, so I'm allowed to use this rule. So this will equal x to the negative 1/2 plus 1 divided by negative 1/2 plus 1. So that was the calculus part. That's the real part of this question. Now I just have to decide, do I need a plus c, or am I plugging numbers into this? And this one is a definite integral, so we're going to plug numbers into this. This is going to go from, what did they say, 0 to 1. And before we plug those numbers in, we might want to clean up that expression. That denominator in the bottom, 1 minus 1/2 is 1/2. X to the negative 1/2 plus 1/2 is x to the 1/2 from 0 to 1. You can even clean this up a little bit more by bringing that 2 in the denominator upstairs. So now I'm going to plug in 1. I have 2 times x to the 1/2. Sorry, 2 times 1 to the 1/2. Well, that's just 2 times 1 minus 2 times 0 to the 1/2. 0 to the 1/2 is 0. So my answer is 2. I want to make a note about this example, about maybe thinking visually about this one. This one is actually kind of interesting. I'll put a little star. So note, the integrand for this example, little f of x, which was 1 over square root of x, is bad. It's not even defined at x equals 0. It's got a weird vertical asymptote there. And yet, we were able to compute its definite integral from 0 to 1 just fine. So what's going on? And if you go back and look at our notes in our textbook for section 6.2 and even 6.1, we're always very careful to say we really want our integrands to be continuous on the interval, and this guy isn't continuous at the point 0 of our interval. So what happened? Well, what happened is it's true that because this guy wasn't continuous, we could have gotten an integral that doesn't exist. What we were trying to compute in that definite integral was the area of this unbounded red region. And what could have happened, this could have had infinite area, and we would say, oh, there's no number. But it turned out that red region that I just highlighted, that red region, even though it goes off forever, this has finite area. And I think we found out that the finite area equals 2. And that can happen. You can have an infinite region that has finite area. It may sound a little weird that that can happen, but what's going on in this picture is that asymptote where all the area is getting higher and higher up, right, where we're getting all that possibly infinite area, it's becoming really, really thin. And it's becoming so thin that it's offsetting how tall it's becoming. Okay, just wanted to point that out, that that's as an interesting visualization. Alright, so here we have some rules that should sound familiar, and if you really think about these two rules that are being stated here, these work for taking derivatives, right? The derivative of a constant is a constant times the derivative, and so now we're just saying they also work for antiderivatives, right? If the derivative of a constant is the constant times the derivative, then the antiderivative of a constant times a function is the constant times the antiderivative. Same thing for the sum and difference. The sum and difference, the antiderivative of two functions being added or subtracted, is the antiderivative of each function then being added or subtracted. So this is a rule you'll rarely say, but you'll use a lot, as example 3 is going to show. So in example 3, it's probably easiest to break this up into several integrals. So this is a definite integral of a polynomial, and the first guy is from 0 to 1, 5x to the 4th, and I can do that guy separately, plus from 0 to 1, 4x dx, and then my third guy I can do separately, 0 to 1, 7 dx. And now I can handle each individual each individual definite integral on its own terms. So this first one, if you want, I can pull the 5 out, right? That was our constant rule. Our second one, we can pull the 4 out. And our last one is just taking a definite integral of a constant. So for each one of these, I'm going to have an antiderivative. So for this one, right, I'm going to do my power rule. So I'm going to add 1 to the 4. That's 4 plus 1 divided by 4 plus 1. And I'm going to evaluate this thing from 0 to 1. For my next guy, I can also think about this doing a power rule. That's x to the 1. So I'm going to get x to the 1 plus 1 over 1 plus 1 from 0 to 1. And then for my last definite integral, the 7 anti-differentiates to a 7 times x. So now I'm going to get these numbers that I've got to crank through. So I'll get 5 times 1/5 minus 0 plus 4 times 1/2 minus 0 plus 7 times 1 minus 0. So if I work that out, that'll be 5 halves plus 4 halves plus 7. And that'll be 9 halves plus 14 halves. So that'll be 23 halves. Okay, let me, maybe in purple or something, sort of write down another way to do this. It's using the same rules, but it doesn't quite so it doesn't take them all the pieces of this apart. So if we're trying to do the definite integral from 0 to 1 of 5x to the 4th plus 4x plus 7 dx, what I wrote in blue over there is totally correct. But if you don't want to break it up and write it out that way, you can just in your head, if you're able to, handle, I don't know why I wrote that, handle each piece. So what I'm going to do is anti-differentiate this guy and write him down there, and then this guy and write him down there. And some people can see this very, very quickly. So if you're one of those people, awesome. If not, you should practice doing it in the quote-unquote blue way. But for right now, some people may have looked at that 5x to the 4th and just saying, oh, I don't need to take the 5 out. I can see what function differentiates down to 5x to the 4th. That somebody started with an x to the 5th. Right, when I differentiate that, I bring the 5 down and I'll get 5x to the 4th. Plus, oh, for 4x, I can kind of imagine what happened. Someone started with an x squared, but had a 2 in front. And then for the 7, well, I know how that works. That's just a 7x. Oh, I think I made an error down below. Sorry, guys. I'll fix it in the blue stuff. I changed something, but oh, so now when I plug in 1, I'll get 1 to the 5th plus 2 times 1 plus 7 times 1 minus, when I plug in 0, I'll just get 0. So when I put everything together, I'll get 1 plus 2 plus 7 is 9. And that should have been my answer from the blue way, so I realize I need to correct something. From this blue way, this was a 5, and I had changed it to a 2 down here. Sorry about that. So now, let me erase this. Sorry about this mistake. Oh well. So now when we do this blue way, I would have gotten 5 times 1/5 is 1, plus 4 times a half is 2. And then plus 7, and I'll actually get 10. And that's what I should have gotten this purple way. It's fun to make mistakes, isn't it? I can't add. Alright, so for this purple way, I would have gotten 1 plus 2 plus 7, so that would have been 10. So I don't know, if you feel very new to anti-differentiating, you probably want to set up your antiderivatives practicing the rules explicitly, like I did in blue. But once you get the hang of it, you might start doing all your work like I've done in purple here. Okay, let's try example 4, and then maybe we'll do a popper question. So example 4 says, hey, well, actually, let's do a popper question right now based on example 4. Popper question 1 is this example 4, an indefinite or a definite integral? And the answer choice A would say, oh, that's a definite integral. And the answer choice B would say that's an indefinite integral. And an answer choice C might say it's both. And answer choice D will say it's neither. Okay. All right, so that's for this. But let's go ahead and now try and compute what's going on with example 4. We have this integral sign, and then we have the square root of x plus 4 times the square root of x minus 4 dx. And when you look at this first, it might look kind of confusing. And really, if it looks confusing, that's good. It should look confusing because if you really think about it, we haven't talked about how to anti-differentiate a product of functions, right? In fact, I don't think we will talk about that quite in that language in Calc 1. In Calc 2, they'll start giving you some ways of doing that. But this looks weird because we're multiplying two things. And so one thing we can do is say, well, what happens if we multiply all that stuff out? So square root of x times square root of x becomes x. I get a minus 4 root x. I get a plus 4 root x. And then I get a minus 16. And so now a lot of that cancels. And this was secretly just anti-differentiating x minus 16. Okay, so here's what I'm going to do. You could break this up into two separate integrals, but I'm just going to write it and do the work in my head that the antiderivative for x is x squared over 2, and an antiderivative for 16 is 16x. Oops, sorry. And then I put a plus c. Okay. So, here are some more rules, right? Basically, the way this goes is, if you know how to take a derivative of some functions, if you have rules for that, then you probably have rules for undoing the derivative. So let's think of these. They list here. Here are all the ways. Here are some indefinite integrals of trig functions. And let's think about this first one. Why are the antiderivatives for sine, why do we write them using negative cosine? And of course I have my plus c, but why do I do that? Well, again, to check why any of these rules are true, all you need to do is take the proposed answer and differentiate it and see if you get the thing you started with. Right, so like down here for the second rule, what's the derivative of sine? Well, the derivative of sine is cosine. So sine is an antiderivative for cosine. What was the derivative for tangent? Secant squared. So now I know how to take an antiderivative of secant squared. And here are my other undone trig rules. Alright, so here's a complicated looking example, but we just want to sort of be persistent. Right, so I'm going to write this out a little bit because it looks funny to me. So it goes from pi over 4 to pi over 2, and that's a cosecant x times a sine x plus cosecant x, all dx. And since this might be new to us, we might look at our rules above and say, well, nothing quite looks like that, right? So maybe what we can do is manipulate this. We're going to go from pi over 4 to pi over 2, and maybe I want to multiply this stuff out and see if it looks nicer. Well, cosecant times sine is just 1, and cosecant times cosecant is cosecant squared of x. And now we might look and say, okay, oh, look at this rule up here. I'm supposed to know what an antiderivative for cosecant squared is. It's supposed to be negative cotangent. So this, I can say, okay, maybe I'll break this up this time. This is integrating from pi over 4 to pi over 2, the constant 1, plus integrating from pi over 4 to pi over 2, the constant cosecant squared of x dx. And now I say, well, an antiderivative for 1 is just x, so that goes from pi over 4 to pi over 2. plus an antiderivative for cosecant squared is negative cotangent x. That goes from pi over 4 to pi over 2. And so that first guy becomes pi over 2 minus pi over 4. Then I have a plus negative cotangent of pi over 2 minus a negative cotangent of pi over 4. So pi over 2 minus pi over 4, that's just pi over 4. And this guy over here is the cotangent is cosine over sine. So negative cotangent of pi over 2 should be 0. And then cotangent of pi over 4 is 1. So with some work, I learned that the signed area under this function that we started with as an integrand from pi over 4 to pi over 2 is this number, pi over 4 plus 1. Okay, so, and now they mention this rule that we mentioned at the beginning of our notes, that the integral of 1 over x is natural log, and you might be a little alarmed and say, hey, what's that absolute value doing there? Well, excuse me, the natural log function is not defined, right, for negative values. And over on this side, I haven't told you any limits of integration, so if you accidentally put some negative limits in there, then I need to switch them around to be positive numbers. But example 6 isn't going to have this problem because the limits of integration are all positive. So the x values are positive, so we'll be able to drop the absolute values. But let's see how this example is going to work. We're going to have the definite integral from 1 to 2, and I might simplify this. I might write this as x squared over x minus 2 over x dx. And that first integral, that just simplifies to x, and there's not much I can do with that second part in the integral. So now we might break this up into two pieces, 1 to 2 x dx minus, and I can pull that 2 out, 2 integral 1 to 2, 1 over x dx. And so this first guy, I just need to remember, how do I anti-differentiate x? Well, I could use my power rule. That'll get me x squared over 2. And fundamental theorem of calculus says, let's evaluate that at 1 and 2. And then how do I anti-differentiate 1 over x? If you want to be cautious, you can write that as natural log of absolute value x. And we're going from 1 to 2. So that first expression turns into 2 squared over 2 minus 1 squared over 2. And this next expression turns into the natural log of the absolute value of 2 minus the natural log of the absolute value of 1. And so here's where you can notice that in my last step over here on the right, the absolute values went away because I was plugging in positive numbers anyway. Alright, so when we do this, I get 4 halves minus 1 half is 3 half minus 2, and I just have a natural log of 2. Because hopefully you remember from practicing a lot that the natural log of 1 is 0. So this is a perfectly good way to leave your answer, but I'll show you one other way to rewrite it, just in case. If this were like a quiz question, maybe they would sneakily rewrite this. So this 2, right, you can use your log power rule to bring that 2 up. Sorry, I don't know why I put an equal sign. So they could rewrite this as 3 halves minus natural log of 4. And if they also wanted, they could say, hey, there's a minus sign in front of here. We could bring that as a power. So this would be 3 halves plus the natural log of 4 to the negative 1, which maybe they could write as 3 halves plus the natural log of 1/4. None of these expressions are more correct than the others. I just want to remind you that there's multiple ways to write our answers. Okay, so what are some other functions that we're used to differentiating now? Exponentials are great because the derivative of e to the x is itself, and that makes e to the x its own antiderivative. Similarly, for a to the x, it's not too hard, right? To undo the rule for differentiating a to the x, rather than multiplying by natural log a, I'll just divide by natural log a. Okay, so let's make example 7 a proper question 2. So the answer choices here are going to be the answers. The answer choices are going to be what are the answers for example 7. So maybe answer choice A would be something like, oh, I don't know, natural log 2 to the x plus 5 e to the x plus c. Maybe answer choice B will be 2 to the x plus 5 e to the x plus c. Maybe answer choice C will be 2 to the x over natural log 2 plus 5 e to the x. And then maybe answer choice D will be 2 to the x over natural log 2 plus 5 e to the x plus c. All right. So we did talk about hyperbolic functions. They've appeared on some quizzes for us. And again, I will remind you, these won't appear on your exams. So integrals of them probably won't appear on your exams either. But it is really easy to take derivatives of these guys, right? The derivative of sinh is cosh, and the derivative of cosh is sinh. So that first one tells us this thing is easy to antidifferentiate. And that second one I said tells us that the antiderivative for sinh can involve a cosh. So this integral, example 8, first of all, I can pull the 1/2 out, and I just have sinh of x dx. And I say, okay, what's a function that differentiates to sinh? That's going to be cosh. And because this is indefinite, I'll put a plus c. All right. In section 4.4, I believe, we told you how to take derivatives of inverse trig functions. That means we now have some rules for anti-differentiating those derivatives. So let me start with example 9. I'm going to rewrite it because the formatting there is a little weird. We're integrating from 1/2 to root 2 over 2, and it's 2 over the square root of 1 minus x squared dx. Well, first I can pull the 2 out. Not that I have to, but I can. And here's the thing. We're now sort of stuck. We look at that integrand and we say, I wonder what I can do with it. Can I think of a function whose derivative is 1 over the square root of 1 minus x squared? And the reason we're asking you to deal with this function is because you've worked hard to practice this, that the derivative of arc sine is precisely this this expression. And so if you can remember that derivative rule, you suddenly get an antiderivative rule for free. This has to be arc sine of x. And we're going to plug in 1/2 and root 2 over 2. So we would need the arc sine of root 2 over 2 minus the arc sine of 1/2. And we can probably, these numbers that we're plugging into arc sine aren't terrible, they're actually okay. The arc sine of root 2 over 2, that's going to be pi over 4. And the arc sine of 1/2 should be, is that pi over 6 or pi over 3? I always get them flipped. That should be pi over 6. And so we get this weird number, pi over 4 minus pi over 6. Let's see. I can factor out a 2, so that's pi over 2 minus pi over 3. The 2's canceled. And so that's 3 pi over 6 minus 2 pi over 6. So this is just pi over 6. Okay. So example 10 doesn't have any integral signs in it. But let's read carefully what it's asking so that you can pick up on the fact that this is asking about antiderivatives. It says you're told that the second derivative of some function is the function 6x plus 2. And then you're told all these conditions. I think I underlined them all too many. You're told these two conditions. If you want to sound fancy, well, before we sound fancy, what you're really being given here is like a little mystery. The mystery goes like this. Somebody's telling you, I'm thinking of a function, but the mystery is I'm not going to tell you. But I'll give you this clue. Its second derivative happens to be 6x plus 2. And then I'll tell you two other little clues about it. Its first derivative at 0 is 2, and its value at 0 is 10. Given all those clues, find the mysterious function. If you want some fancy way of saying this is what's called an ordinary differential equation. And the only reason I make a big deal out of this is a lot of you might go on to take this course. It's super useful in a lot of science courses. So the abbreviation here is this is an ODE. It's an equation, and the equation here is f double prime of x equals something. But rather than all the other equations you've studied so far in most of your math courses, the solution isn't a number. The solution is a function. What function satisfies this? Well, what we really need to say is, first off, I need to think of a function whose second derivative satisfies this. That means its first derivative would have to be an antiderivative of all this stuff. That's the key thing here. So its first derivative would have to be one step undoing this. And we could say, oh, okay, I know what its first derivative would be. The first derivative would be, I know how to antidifferentiate 6x. Let's see, that's going to be 6 times x squared over 2. And I know how to antidifferentiate 2. That's just 2x. And then I put my plus c. But when I go and write this out, I'll get 3x squared plus 2x plus c. So notice we're one step closer to solving this mystery. We didn't find the original function yet, we found its first derivative. But I want to point out something. We haven't completely found its first derivative, right? Because we have this silly constant plus c. And so really to know this actual first derivative, I would need to use some condition that tells me how to figure out what c is. And to figure this out, right, I'm going to use the fact that they told me f prime of 0 equals 2. So when I plug in 0 into this first derivative, I'm supposed to get 3 times 0 squared plus 2 times 0, and then I have my plus c, and that's supposed to equal, what did they say, 2. So what this tells me is c equals 2. Right, so that first condition helped me. I now know that whatever function they were thinking of, its first derivative had to be 3x squared plus 2x plus 2. That's the first derivative. Now once I have that, I can say, okay, well, the actual function is an antiderivative of that first derivative, 3x squared plus 2x plus 2 dx. And now I say, okay, I know how to do this. This is a great place for you guys to pause and work this out yourself, but it does work out this way. The antiderivative of 3x squared works out to be x cubed. The antiderivative of 2x works out to be x squared. The antiderivative of 2 works out to be 2x. And then I've got to put a plus, and I'm going to call it capital B since I already used C. Some other constant, right? And to figure out this constant, we need to use our second condition, f of 0 equals 10. If we plug in 0 into our expression for f, we're supposed to get 10. That's going to be 0 cubed plus 0 squared plus 2 times 0 plus b. If you work all that out, you learn that b equals 10. And so our final answer here, maybe we'll write it in purple, is the function they were thinking of had to be x cubed plus x squared plus 2x plus 10. And so there's a whole course on what we call ordinary differential equations, solving these function mysteries where the clues are in terms of derivatives and conditions. But most of them are not as straightforward as equations like this, because we can just use calculus, the fundamental theorem of calculus, to get these done. Differential equations is all about other more interesting equations, like maybe can you find a function whose derivative is 1 over itself? That's suddenly a little trickier than the type we just practiced. But okay, still, example 10 is an example, if you want to sound really fancy, of a second order differential equation. Okay, before we do this integrating piecewise defined function, let's do a third Popper question. So Popper question 3. Let's just practice this. What is the indefinite integral of 1 over 1 plus x squared? And the one thing I want to point out, I wrote the dx on top there. You can write this as I wrote it or like the second way. These are all the same. So what I'm asking for is, can you think of a function whose derivative is 1 over 1 plus x squared? And the first answer I'll offer is maybe the arctangent function. The second answer I'll offer is maybe tangent. The third answer we'll offer is maybe 1 plus x squared, and then maybe an arcsine. Okay, so this is a good one for you guys to think about. Oh, all of these are wrong, sorry, because on all of them I forgot a plus c, right? Because these are indefinite. These are answers to indefinite integral. Okay, let's try example 11. It says, let f of x be a piecewise function. Let's set up, we don't necessarily have to actually evaluate it, but let's set up the integral needed to compute this definite integral from -2 to 2 of f of x. So here's the thing, right? This is really just having us practice with piecewise functions. In our integral, right, x is switching values. It's sliding through -2 to 2. And our function, f of x, changes its formula depending on what x is. So the way I would set this up is I would, of course, break up this interval from -2 to 2 using the intervals where my function has different formulas. right? So maybe we can color code some of this. So maybe it's x plus 2 on this orange interval. So I would go from -2 to 0, and I would use x plus 2 dx. And then from 0 to 1, maybe it switches to this green formula, 2, on the interval from 0 to 1. So that would go from 0 to 1, that would be 2 dx. And then the last piece, I would naturally break it up, goes from, let's see, it's going to switch over to this blue formula, 4 minus 2x, on this blue interval between 1 and 2. So it'll go from 1 to 2, and it'll be 4 minus 2x. All of that dx. Now we could actually evaluate this, but the point is, this function, right, its formula changes depending on the interval of x values you're letting it take in. So its definite integral changes depending on what intervals that definite integral includes. Yeah, so let's try example 12. Maybe somebody says, hey, compute the definite integral of like an absolute value function. And over here on the right, these typed notes remind us how to think about the absolute value function as a piecewise function. So what they show us here is y equals x. And maybe we'll color code this, and I guess I'll use blue. The absolute value, f of x, is really this thing. So what I should maybe do is say, okay, in blue, it's this curve, and then it's this line. So that would be y equals the absolute value of x in blue. So it's that v. So if you want to think of example 12, it says, hey, compute the definite integral from -1 to 2 of absolute value of x dx. And you can absolutely break this up as, well, when the inputs are negative, the absolute value function is negative x. That makes them positive, right? Plus, then when the inputs are positive, we just get x dx. Right? We broke it up over each interval according to this piecewise definition of the absolute value. Okay, so here I would say, okay, this is negative integral from -1 to 0 of x dx plus the integral from 0 to 2 of x dx, and this now becomes negative x squared over 2 from -1 to 0 plus x squared over 2 from 0 to 2. So I believe I get from there negative 0 squared over 2 minus 1/2 plus 2 squared over 4 minus 0. So that becomes a 1/2 plus 4 over 4. So that just becomes 3/2. And you can totally do this off to the side here completely visually. Let me maybe draw this absolute value function in a little better. What this original definite integral was asking for was the area under the absolute value function, so this area, starting at -1 and ending at 2. Well, because this graph has straight lines, the area under it just involves triangle formulas. So we could have done this one visually, thinking about triangles. We could say the area of this piece, right, it's signed area, but it's all above the x-axis, so it's all positive. The area of that piece should be 1/2 base times height, so it's 1/2. the area of this piece over here should be 1/2 2 times 2, so that should just be 1/2 2 times 2. So when I work that out, that's 1/2. Oh, did I make a mistake? I got 1/2 plus 2, so maybe I made a mistake somewhere. I got 5/2. Let's see where I made a mistake before. Oh, I see where I made a mistake. Sorry, guys. Over here, I'll circle it. Over here, this is x squared over 2. That's correct. But then I wrote it as over 4. That's where it's wrong. So this needed to be over 2. Sorry about that. So that's 2 squared over 2. So that was 4 over 2 for that piece. So that would be 4 over 2. So I would get 5 over 2. It's kind of interesting doing it visually. I didn't make a mistake, but setting up with integrals I did. It's good to practice both ways if you have time to. Okay, so here's a good one. Set up the integrand needed to integrate this thing. Okay, so they have a graph here, which is actually pretty helpful. And let me just go ahead and show you. Maybe I'll try and do it in green. What the integrand looks like, what its graph would look like in green. So it would be this, but suddenly here it wouldn't go negative because you're taking the absolute value. So it would actually do something like this. Right, so in terms of visualizing this, like we did our previous example, the area represented here would say it starts at 1 and it goes up to 5, so it would be this area that stops at 4 and then gets up this additional area. So that's what this green definite integral represents, is all of that positive area. Okay, but let's think about how we would set it up to compute it. The graph they gave us is really helpful because, let's see, x squared minus 3x minus 4, I think we can factor that as x plus 1 times x minus 4. And what this is telling us is that this function, when I take the absolute value of it, right, it's going to break this up into two pieces, or several pieces. This is going to equal, well, if we are before -1, it's just going to equal itself, because before -1 it was positive. But if we're in between -1 and 4, then it's got to be the negative version of itself to flip it up. And then after 4, it's just got to be itself. Right, so their graph giving us that information can help us see that. And so if we want to integrate from 1 to 5, this absolute value thing, we really want to break this up into the intervals where it has to switch between being itself and being negative itself. So from -1 up till 4, so it's the up till 4, right? We need to break this up from, this one doesn't start at -1, but it goes from 1. We need to stop it at 4. And then from 4 to 5. And so now we can say, okay, from 1 to 4, you have a negative sign in front of you, right? Because that's what the absolute value is doing. So I get a negative sign there. And after 4, the absolute value doesn't care because this function is positive anyway. And so this is what we would want to finish computing for this question. Maybe I'll do the first one. That'll be negative. And the antiderivative for x squared is, of course, x cubed over 3. For 3x is minus 3x squared over 2. And for 4 is minus 4x. 1 to 4. And then the next piece would be an x cubed over 3 minus 3x squared over 2 minus 4x, and that would go from 4 to 5. Right, so what's happening in this picture is all of this stuff here, this would have been recording this negative red area. But then, because it had an absolute value, this part gets a minus sign to flip that negative area into this positive green area. And this stuff over here, we don't need to put any sort of weird thing in front of because it was already this positive green area. Okay. Alright, so let's maybe try this one. The integral of the absolute value of x squared plus 4. And so let me just show you, absolute values can look tricky. So how do I think of the absolute value of some function more generally? Well, especially when integrating this thing, it is helpful to write it as a piecewise function. So the absolute value says, hey, I'm always going to make you not negative. So I'm going to leave you alone, not going to do anything to you, if g of x is positive, but I'm going to stick a minus sign in front of you if you're negative. And here's the trick, right? If g of x, whatever we shoved into this absolute value function, is weird, we might have to do some work over on this side because we really want these two things to be in terms of x. So if I go back and ignore, say, well, I'm plugging in any function, let's do this with the function we were given here. Maybe I have x squared plus 4, like I was told to use. Well, then it's going to be x squared plus 4 whenever x squared plus 4 is positive, and then I got to put a minus sign in front of it whenever x squared plus 4 is negative. And I'd really like to get these things I've underlined in orange in terms of x. So this can feel like maybe a fun or annoying or whatever review of solving some inequalities from college algebra. But like, I want to know, when is x squared plus 4 bigger than 0? I'd like to solve this for x. That is, when is x squared bigger than negative 4? And you might notice, wait, this is always. Can't spell always. Whenever you take the square of a number, of a real number, you get something bigger than negative 4. Let's look at that second condition, see if we can rewrite it in terms of x. When is x squared plus 4 negative? That is, when is x squared less than negative 4? Never. So this one never even happens, the second thing down here. This never happens. What we just found out is that the absolute value of x squared plus 4 is equal to x squared plus 4 for all x. So if x is between negative infinity and infinity. And if you really think about it, well, of course it is. X squared plus 4, this function was already positive, so taking an absolute value of it didn't do anything. So this was sort of a fake out question. We're going from 1 to 5 of x squared plus 4 in absolute values, and if we think hard about that function in the absolute values, we say, wait, you didn't even need those absolute values, so we're just x squared plus 4 dx, and so this would just be x cubed over 3 plus 4x from 1 to 5. So that would be 5 cubed over 3 plus 20 minus 1/3 plus 4, whatever that works out to be. So I think there was a typo on there. I'm going to assume what they meant was try this one, integrating from 1 to 5, the absolute value of x squared minus 4 dx. And so we can think about this. The absolute value of x squared minus 4, sometimes it's good to break these up and factor them. What we see is that this thing is going to need to be fixed before or after 2 and negative 2. So if you really think about this guy, this is going to be x squared minus 4 is going to be itself if x is less than or equal to negative 2. It's going to be itself if x is bigger than or equal to 2, but we're going to need to fix it with a minus sign if x is between negative 2 and 2. So for this definite integral, we'd want to break this up going from 1 to 2 of x squared minus 4 dx, plus, and then we want to pick it up going from 2 to 5 of x squared minus 4 dx. And so on this part, we would get, oh, that becomes negative. And then on this part, we get to leave it alone. And visually, of course, I always like to think visually when there's time to. So we're going, let's see, maybe that's negative 1, negative 2, negative 3, 1, 2, 3, 4, 5, 6. So x squared minus 4 as a graph is just this parabola that looks something like this. And so the absolute value, which maybe I'll draw in blue, looks almost the same. It just stops here. You flip this hump over, and then you go there. And so we were being asked to compute all of this blue area from 1 to 5. So it was this blue area here that we needed to add this extra minus sign to make sure it would be positive area. Okay, let me add in one little page for some last poppers. A second here. I think we can have like 2 little poppers left. So popper question 4, I believe we're on. Let me scroll up and make sure we're on 4 and not 3. Sorry for anybody who's epileptic. Oh, we're on 3. Good thing I checked. Yeah, good thing. Oh no, we're on 4. Okay, cool. All right. So popper question 4. Let's see. Let's try evaluate the definite integral from e to e squared of 1 over x dx. Is it answer choice A? Oh, is it E? Is it answer choice B, the natural log of 2? Is it answer choice C, 1? Is it answer choice D, 2? And is it answer choice E, none of the above? Okay, that's just one last little popper question, and then to get to our final one, our actual last one, Popper question 5. This is sort of a review one from 6.2. So this would say, okay, what is the x derivative of the integral that starts at pi and that ends at x squared of e to the 1 plus cosine of t all times t cubed dt. This looks horrible, but let's give ourselves some answer choices. Is it answer choice A, e to the 1 plus cosine x squared times x to the 6 times 2x? Or is it B, e to the 1 plus cosine of x squared times x to the 6? Or is it C, is it e to the 1 plus cosine of x times x cubed? Or is it D, all of the above? Alright, I'll see if I have time to post any other videos. Certainly I'll be trying to post some review videos when exams are about to come up, but hopefully these have helped you get through our course. I hope everybody's staying safe, and I hope to see you in the fall.